Okay.
So, I want to use this brief presentation to introduce the topic about tolerance analysis and tolerance management. And what we are going to see today is the way to perform the tolerance analysis. And tolerance analysis during the product development process is a very important topic. And it is, let me say, the only way that today we have to find a compromise between different requirements. And those different requirements are related to the need from the design point of view to obtain high performances of our product. But on the other hand, we need to find a compromise with the requirements from the manufacturing processes, because from the design point of view, the tolerances must remain as small as possible to obtain the best performances related to our product and to obtain the best quality related to the products that we need to develop. But on the other hand, when it comes to manufacturing processes, we would like to have a very large tolerances, because in that case, we can produce parts and components at a lower possible cost. But we must consider that in that case, the quality, the final quality of the assembled product will be compromised. So we need to find the best compromise between those two different requirements, and the tolerance analysis is the only way that today we have to find this compromise. When it comes with the tolerance analysis, we must be aware also about the fact that several times the tolerance analysis is performed using a spreadsheet, using a simplified approach. It is called the worst case approach. It is performed with one-dimensional tolerance analysis. And this is related to the fact that tolerance analysis, when it comes with three-dimensional statistical analysis with statistical variables and with the geometric tolerances involved in the tolerance chain, it is a very difficult topic. It is a very difficult calculation model to manage. And for this reason, several times it is performed using the worst case simplified approach, because there are no other way to solve this type of calculation. So in this case, if we want to obtain reliable results, we need to perform the simulation about the tolerance chain, the simulation using a three-dimensional model with statistical variable and with the usage of geometric tolerances. This is the only way to obtain reliable results. And in this particular case, the only way to perform the simulation is to use a software, because otherwise you cannot perform this type of calculation without a software. Sorry, without a software. So today I want to show you a live demonstration about CETOL. CETOL, it is the software that we have here in EngineSoft to perform this type of analysis. And I want to show you a live demonstration about this software using this product. It is called the CETOL. And we are going to study not the whole product, but only this product configuration. This product configuration is the open one, because this purple part is in touch with this yellow stop pin in my seat latch. And from the tolerance point of view, from the tolerance chain point of view, we are going to calculate this functional requirement. It is called the clearance. And we want to have the clearance always positive. So we want to study the tolerance propagation inside this three-dimensional product to understand which is the risk to have a negative clearance, because we don't want to have a negative clearance, otherwise our product requirement will be negative in this case. So once defined the aim of my analysis, I can go directly inside the software to show you which is the way to create the tolerance chain and to solve it. And most important, after the creation of the tolerance propagation model, we will see how we can read the results. And most important, we can see how we can take, or we can discuss about corrective actions that we can apply on our design. And for design, I mean three-dimensional nominal CAD model and the dimensioning schemes present inside the technical drawings. And we can see which are the best corrective actions that we can apply from the tolerance point of view to obtain at the same time a robust design from the tolerance point of view with the higher value for the tolerances possible in this case. So for the calculation of the clearance, we can, based on our three-dimensional nominal CAD model, as you can see here, we are in a PTC Creo environment, but consider that you can replicate almost the same behavior in the creation of the tolerance propagation model also in other CAD environment, for example, in SolidWorks, for example, in Siemens NX, for example, in Dassault CATIA V5, for example. So, first of all, let's build up our tolerance chain analysis. So let's create the tolerance propagation model. The first thing that we need to do is to, using this tool, the add component tool. Sorry, let me check only if the properties are correctly defined. Yes, okay. So, okay, so we can start with the add component tool, the add component with the add component command, and we can, after the selection of the add component command, we can select here the CETOL and start to import the first part. It is called the side plate. Then, after the side plate is inside our tolerance propagation model, we can move to the second part, and we can press the Add Component button, selecting the stop pin, the yellow stop pin. And after the selection of the yellow stop pin from the nominal CAD model, this window appears. In this window, we can read which are the mating conditions defined in the nominal CAD model between the side plate and the stop pin. And we can decide if we want to import those assembly conditions or not inside the tolerance propagation model. Since I don't want to repeat something that I already created in my CAD nominal model, I confirm the selection for the import of both these joint conditions, and I can move on to the next step in the creation of my tolerance analysis model. The joint conditions are defined here in the CETOL tree with these icons, purple and yellow colored. And for sure, I can, inside the joint properties windows, I can set or I can change a lot of different options to customize to customize the joint properties for between the stop pin and the side plate. Consider that in a tolerance propagation model, the definition of the joints, the so-called joints, are used to define in which way the parts are touching together. And this is really important in a tolerance propagation model because this governs how the errors, the tolerances, propagate inside the tolerance model. So it is a way to define how errors move from one part to another inside our assembly. I can then move to the next part and import this second yellow pin. Another time I can decide if I want to import or not the mating condition between these parts. And another time I can confirm my choice. And as the last part, I can import this claw inside my tolerance propagation model, considering also in this case the joints present inside the native assembly CAD model. Right now, we are almost at the end of the creation of our assembly model. Right now, I can see that the software with this yellow arrow, the software, the analysis, CETOL, is telling me that the claw, the purple part, is free to rotate around the centering pin. And I can see this information also here in the bottom right part of the screen, where I can see from a kinematic point of view that there's an under one condition. It means that the part, the claw, is free to rotate around the centering pin. Now, I don't have inside my native CAD model a mating condition that constrain this type of rotation. And so, in this particular case, I can use the functionalities of CETOL to adding a joint to the previous one. The way to create a joint inside CETOL, it is very fast and easy because you only need to click on this tool and then click on this surface and then on the second one. So after the selection of these two surfaces, you can confirm the definition of this joint. And this means that when we will perform the tolerance analysis, the solved configuration will be this one. If we compare the configuration with the one present inside our slide, we can see that the configuration, it is completely the same. Now we can move as last topic to the definition of the clearance, to the definition of our functional requirement for our simple product. Then we can, for example, click on add measure, and we can ask to CETOL to calculate the variation of the distance between this surface and this one. We can confirm our choice here because we can change the properties related to this output measurements later during the preparation of the model. And we can see, using this tool, the show button, we can see which is the clearance already defined. Taking a look at the current definition of the clearance, we can see that the software is behaving in its default condition. It means that it is taking into account the lower distance between the two selected surfaces in the configuration defined with the joint present in the tolerance propagation model. If we compare this clearance with the one present in the presentation, it is clear that we need to change this definition. And in CETOL, for example, we can use the properties related to the definition of the clearance to change, for example, the orientation of this output measurement. We can ask, for example, to calculate the clearance between the two selected surfaces, but always in a direction perpendicular to this surface. When you confirm your choice in your definition, then we can check that the clearance now it is correctly defined based on the functional requirement that I need to calculate. Right now, the last thing to do before running the analysis is to set for this clearance, for this functional requirement, is to set a quantitative value related to this requirement. And in this particular case, since we want to obtain always a positive clearance, our requirement, it is quite easy to set because we only need to define a lower limit of 0 millimeter because we want to avoid interference of the claw with respect to the other part present in the tolerance propagation model. So this is the requirement defined for the clearance. And now we can move to the calculation of my tolerance chain, and we can take a look at the final results and discuss the most important topic, that is the definition of the corrective actions that we can apply during the design phase of this product to obtain a robust design from the tolerance propagation point of view. To calculate the final results, you only need to click on Solve, then OK, and your tolerance chain, it is ready to be checked based on your final results. These are the results obtained for the clearance. Now, before starting the discussion on the final results, we can take a look, for example, inside the side plate, and we can see that inside the side plate model, the dimensioning scheme for the part, it is already defined. And the reason for that is that the side plate as a single part, I can open it, and we can see that the dimensioning scheme, it is completely defined with three-dimensional annotations. So this means that if you work with a model-based definition approach, creating the technical drawings related to single parts directly inside your CAD model, your native CAD model, Creo in this case, you can automatically transfer all this information to CETOL for the calculation of the tolerance chain. So CETOL, it is a software that it is a model-based definition ready software because it can automatically import all the annotations related to each single part. You need to define it in a proper way. So you need to define semantic three-dimensional annotation, but once you defined it, you can use them and you can import them also for your tolerance chain calculation. Let me now close this model. Sorry, one moment. I'm going to share the screen again. Okay. So we can now come back to the results related to the clearance, and we can start to see how to read and to use these final results to obtain and to apply the most reliable corrective actions to my design and to my product definition. So, as you can see here, in a few minutes, we solved a very complex tolerance propagation model, because there are more or less, let me say, more than 50 contributors about tolerances in this tolerance propagation model. We are talking about a full three-dimensional tolerance chain with both dimensional and geometrical tolerances inside. And we have here the results from the worst case point of view and also from the statistical point of view. Now, it is clear there are several different reasons that lead to manage this type of results from the statistical point of view, because if we use the statistical approach, we can obtain a better compromise between the product requirement and the development cost. We can define the tolerances inside our technical drawings in a better way, obtaining a tolerances with a width that it is more representative to the real requirement of our product. So let's discuss the results related to the statistical distribution, to this statistical distribution. And as we can see here, this result is defining something with poor quality. So the clearance here, there's a relative high risk to obtain a negative clearance related to the tolerance value inside my tolerance chain. And I can see this risk here, taking into account the red area of my statistical distribution, that it is the red area, it is the area below the zero value. So it is something related to a negative clearance. How can I define this risk in a quantitative way? I can see this quality matrix inside this box, and I can quantify the red area of my statistical distribution using this value. It is clear right now that if I am designing my product right now, I can, taking a look at this result related to the clearance, I can understand that the risk to have a negative clearance, it is quite high. And if I am in the designing phase, what I want to obtain is a reduce related to this risk. So I want a reduction of the red area related to my statistical distribution. And right now, we need to understand how, and this is quite important, we need to understand how to reduce the red area of my statistical distribution in the proper way. So one possible way to reduce the red area is to reduce the width of the statistical distribution. So when I talk about the reduction of the width of the statistical distribution, I am talking about the standard deviation related to this Gaussian curve. It means that if I want to reduce the standard deviation, I need to reduce some tolerances inside my technical drawings. But now the question are, which are the tolerances that I need to reduce, and which is the final value for these tolerances? Because these are both a very important topic to obtain the compromise between quality, between final quality for my product and the development cost related to the manufacturing processes. In CETOL, once you have your analysis available, it is very easy to understand which are the tolerances that you need to take into account to lower the standard deviation related to the Gaussian curve. And it is very easy to find which is the final value that you need to use for these input tolerances, because you only need to take a look at the contribution analysis. Inside the contribution analysis, you can find a ranking of the tolerances with the most impact on your final requirement. So it means that if you want to change one tolerance, it is better to start from 1, 2, and 3, because they are the most impacting tolerances on the final requirement. It has no sense to change and to lower this tolerance, because, for example, in this case, the final impact will be very, very small, without affecting in the proper way your final results and your product requirement. So, for example, once you understand this behavior, you can start your simulation. For example, what happens if I take this position tolerance of 0.7 and I move it to 0.5? I can press enter and I can immediately see which is the final result related to this decision. And then I can move to change another tolerance and, for example, another one. If this is not enough, we can reiterate this behavior. We can change another time our tolerances. For example, let's start from the first one, and you can simulate what happens if I move this tolerance from 0.5 millimeter to 0.3 millimeters, for example. And as you can see, every time you are lowering one tolerance value, the red area related to your statistical distribution becomes smaller and smaller. It means that your final functional requirement will be satisfied in your final product. And then you can decide, based on your need, based on the requirement related to your clearance, you can decide where to stop, or you can decide which are the most appropriate tolerance value to be used case by case. This is only the first possible corrective actions that you can apply to your clearance, to your product requirement in this case, because we are now changing the tolerance value. But this is not the only possible corrective action. And now I want to show you the second possible way to improve the reliability of your product and to obtain a more robust design. For this, I want to come back to the starting situation in my tolerance propagation model. Okay, this one, because there's another way in this particular case to improve the reliability of my product requirement. Because for example, in this case, we were lowering the standard deviation related to the statistical distribution, but there's another way. We can keep the standard deviation as is, and we can simply move our statistical distribution to the right side of the screen. So in this case, I am not talking about a change on the standard deviation, but I want to change the mean value for my statistical distribution. This is quite important because the change about the mean value, it is not related to the change on the statistical distribution. And this means that you can keep your tolerance value at the starting point without the need to lower the tolerances inside your technical drawings. So this second way, this second type of corrective actions, it is the most effective one when you can use it, as in this case. When you can apply it, it is the most important one. And how can I change the mean value related to my statistical distribution representing the clearance right now? The way you can change the mean value is changing the nominal distances, the nominal dimensions inside your CAD model. Keep attention, because in CETOL, you cannot directly change the dimensions related to your nominal CAD model, but you can simulate a change about this dimension. Then, if you see that a change or some changes can help the robustness of your final design, of your final product, then you need to come back to the CAD model and to implement these changes. How can I simulate in CETOL a change on my nominal CAD model? It is simple because I only need to take a look not to the contribution analysis like we did before, but to the sensitivity analysis. The sensitivity analysis, it is another ranking available in CETOL where you can find the impact of each nominal dimension, or better, the impact of the variation of each nominal dimension on your final requirement. For example, here you can find several different nominal dimensions. You can also see which are the nominal dimensions inside your nominal CAD model. And then once you find a nominal dimension that it is easy to change for you, and it is a good dimension to apply a change, a very good dimension to modify, then you can simulate a change on this dimension. For example, let's take into account this dimension. This dimension is inside the side plate part, and the nominal value, it is 12.56 millimeter. This dimension, this nominal dimension, has a negative sensitivity. It is colored purple here. It means that if I change this dimension, increasing it, I have to expect that the mean value will be lower, and so it means that my statistical distribution will move to the left side of the screen. But I want to avoid this behavior because what I need to obtain is the movement of my statistical distribution to the right side of the screen. So now I know from my tolerance analysis, I know that with a negative sensitivity, I need to move the statistical distribution to the right side of the screen, and to do this, I need to lower this value related to this nominal dimension. How can I perform this simulation? I only need to click here, and I only need to change the mean value related to this input variable. For example, what happens if I change this dimension? Consider that this is a simulation. What happens if I change it from 12.56 to 12.4? And you can immediately see which is the feedback about your statistical distribution. Then you can say, what happens if I move it to 12.2 millimeters? And to 12 millimeters? And to 11.7 millimeters, for example. And as you can see, every time you change or you simulate a change in your nominal dimension, you can see that your statistical distribution related to the clearance move to the right side of the screen, and that you are obtaining every time a more reliable design. A more reliable design, a more robust product, because it is now a product that it is less sensitive to the variation due to the tolerances in your technical drawings. Right now, when your product it is robust enough, you can come back to the contribution analysis, and you don't need to lower the tolerances like we did before. But now you can simulate an increase in the tolerances, because now you have a robust design and you can admit tolerances with a width that is higher with respect to the one used as starting input values. So at the end, you can replicate this same behavior. You can replicate this exactly the same consideration for all of the product requirement and for all the products that you have to study from the tolerance point of view. You can always find the better compromise between the final quality related to the functional requirement of the products and the tolerance values inside the technical drawings that you need to send to the manufacturing processes. In this way, this compromise allows you to have final product, reliable final product, robust with respect to the tolerance variation, but at the same time with the minimum possible product development costs, because you have in the technical drawings the width of your tolerances higher enough to lower down the manufacturing costs. And the way to do this is to perform tolerance chain with a reliable tool, and CETOL is a very reliable tool for the resolution of the tolerance chain analysis. And it is also not only reliable, but also it is very effective because, as I already demonstrate, you can solve very, very complex three-dimensional tolerance chain using statistical variables, using both dimensional and geometric tolerances in few minutes. And so you can obtain a lot of information, a lot of data from your tolerance analysis, and from that data, you can improve your product, you can improve your design, and you can obtain better products at the lower possible development costs. Thanks everyone for joining this webinar. And if there are any questions related to this software, I can try to answer that. Or otherwise, yeah, we can close and you will receive the link to download the registration of this webinar. Thanks to everyone. Another time. See you soon.